Can you see the screen? Can you guys see the screen? Can see the screen? Hello, can you guys see the screen? Yes, no? Okay. Okay. All right. Let me start with chapter 2. Okay. What we have done so far in chapter 2. Of course, chapter 1 we have finished before the MCO. So in between of chapter 2, the MCO start and the physical appearance in our classes stop. We go by online. Now, what happened in chapter 2 is we went through this. Okay, this is first part in chapter 2. If you notice, I have went through optimal solution and optimal value for you in example 1. And this, please recall back. We have I asked you to draw in the graph and asked you to find this optimal solution, all these things. And we have also done exercise 1, 2, and also minimum maximum problem, all are done up to here. Okay, up to here I have done with you, and this is actually your chapter 2. Okay, the introduction to linear programming is ending here. So the moment the next part, range of optimality, the moment we enter range of optimality, that is actually your chapter 3. Okay, this is chapter 3, linear programming, and this is known as sensitivity analysis. Okay, this is your chapter 3. So range of optimality I have done with you in the class also. Okay, we have done range of optimality in the class. I have done a detailed computation with you all regarding the range of optimality. Remember, this is something to do with your gradient. Okay, now after range of optimality, the next part is range of feasibility. So range of feasibility need more detailed computation compared to range of optimality. Okay, so for this purpose, I'm expecting a physical presence of all of you in the class. So I will hold on this for a while, range of feasibility. Once we come back as normal, once MCO finished and we come back, we meet in the class, hopefully I can go through this with you. Okay, so for the time being, hold on this. And today we will go on with standard form. Okay, so let us move on to standard form today. Give me a moment. Just give me a moment. Somehow my connection interrupt. Please give me a moment. Just now it was connected. Now it is not connected. Can you see the screen? Can see the screen? Sorry, I need to double check. Can you guys see the screen? My slide. Okay, okay. I just need to double check. Okay, for us to go through the standard form, okay, this is standard form. See, just look at this example here. Standard form is a method to write the inequality, all the inequalities to equations, okay. A plus B less or equal to 10. 3A plus B less or equal to 24, and A plus 2B less or equal to 16. This is the inequality. So how we going to write this is an equation. You see, A plus B is less than 10. If I want to write this in equation, I need to plus here some number. Okay, for example, 3 less than 5. If I want to make it equal, I must plus 2 here. Okay, I need to plus 2 here to make sure this is equal. Therefore, I need to plus some number here. Let us denote that number is S1, then this one become equal. This one become equal. This one become equal. Okay, so that's how you make inequality to equal, by just adding a variable here, S1, S2, S3. This S1, S2, S3, this variable is known as slack variables. Okay, slack variables. So how to do this? Whenever you see inequalities, whenever you see linear programming, the question asks you to change to standard form, you just plus some variables here. We will denote it as S1, S2, S3 and write it as slack variables. Okay. Now after this, our objective function here is maximize maximize 3a plus 2b. Now this is objective function with a, b, okay, plus 0. Now we have extra variable here. We're going to add S1, S2, S3 in the objective function. Okay. The next step would be, after writing S1, S2, S3 in the constraint, the next step would be writing this, integrating this variable into the objective function. How we're going to integrate? We will write S1, S2, S3, but right here 0. Okay, the coefficient is 0. That's how you integrate with the objective function. And we need to integrate also to our non-negativity function a comma b. If there's no slack variable, it is just greater or equal to 0. If there is slack variables, S1, S2, S3, so greater or equal to 0. Of course, you have to write here subject to. Subject to, okay. So this is maximize 3a plus 2b plus 0 S1 plus 0 S2 plus 0 S3. subject to all these constraint, and this is the slack variable, and this would be your non-negativity constraint. Okay, this how you change your linear programming model to standard form. Okay, so the answer is also given here in my slide. I will later share this slide in the group. You can see. All you have to do is plus S1, S2, S3, and then change according whatever we have done just now. Okay, this is standard form. Now, after standard form, we are going for shadow price. All this is still in chapter 3, sensitivity analysis. Okay, we are going for shadow price. Shadow price, or also known as dual value. Okay, what is this shadow price or dual value? Let me write the definition first. The value of improvement in optimal value by increasing 1 unit of resources in the binding constraint. Okay, so this would be the definition for shadow price or dual value. The value of improvement, I would like to underline this word, improvement in optimal value by increasing 1 unit of resources in the binding constraint. Okay, we are going to focus on binding constraint only now. Okay, now let us look at example 1. Let us show you how to calculate shadow price by looking at one example. When we do this question, first example, what would be the binding constraint? Okay, the binding constraint here is, if you look properly, the binding constraint is the constraint develop the optimal solution, that is C1 and C2. So right here C1 and C2. C2 is 3A plus B, C1, C2. This would be your binding constraint. Okay, this is of course a maximum problem. By having this binding constraint this is the binding constraint for the example 1 we have done. What would be the optimal solution? If you notice, optimal solution is actually 7.3. Optimal value is actually 27. When I say maximum, it is actually your profit. Remember that. Okay, maximum means we will only maximize whenever you have a profit. Okay, now according to the definition, can you see the screen? Can you guys see the screen? Can see the screen? Now can? Okay, let me repeat again. Let me repeat. This is the shadow price. The definition of shadow price is the value of improvement in optimal value by increasing 1 unit of resources in the binding constraint. So if you read this, of course, you won't get the answer. You won't get the idea how to get the answer. Okay, let us go through this by an example. In example 1, when we solve, C1 and C2 is the binding constraint. C1 and C2 is the binding constraint. An optimal solution is 7.3 and optimal value is 27. Okay. Now, let us write again the binding constraint here. C1, C2. I'm writing the binding constraint in terms of equation now. Okay. Now, according to the definition, what is the shadow price is if I increase 1 unit of resources in the binding constraint, we want to see what is the improvement in the value, optimal value. So how is this be done? A plus B equal to 10 here. Okay. I'm going to write here, I'm going to increase 1 unit in 10, which means I will get 11, sorry. Okay. In 10, if I increase by 1 unit, I will get 11. And then 3A plus B is 24. So I will get here 24. I'm only increasing 1 unit in C1. C2, I write the remaining thing, whatever is there. Whatever is written there, I write there. Okay, no changes in C2. C1, I increase by 1 unit. Okay. If I increase 1 unit in C1, how the value will be? How the optimal value will be? So let us try to solve this. I'm doing elimination method. Okay. I'm going to solve this A and B. So if I do this, I will get 2B, 9, B equal to 9 over 2, which is 4.5. From 1, my A will be 6.5. So my new optimal solution now, when I increase 1 unit in C1, is 6.5, 4.5. If my optimal solution now 6.5, 4.5, remember original was 7.3. Now this one 6.5, 4.5. What will be my optimal value? My optimal value is 28.5. Now, you tell me whether is this an improvement or not an improvement. Previously, our optimal value is 27, okay, with 10. I increase 1 unit in the resources. This is resources. This is the resources for C1 on your right hand side. When I increase 1 unit in the resources of C1, which is the first binding constraint, I increase 1. Our profit increase or not? Yes, isn't it? So this is an improvement. You are happy. As a businessman, you are happy because your profit has increased. Therefore, this is an improvement. How much it has improved? Take the new value minus the original value, you will get 1.5. Remember, take the new value minus the original value, you will get 1.5. Therefore, the shadow price or the dual value for C1, binding constant 1, is equal to 1.5. Okay, 1.5. Because this is an improvement, you write here 1.5. How much is an improve? 1.5 ringgit or dollar. Okay, hope you guys understand. It has increased your profit. How much is increase? That is your shadow price for C1. Now let us do the same thing for binding constant 2. Now A plus B, 3A plus B. This is C1, this is C2. Okay. Just now I increase here. Now I'm increasing here. This one remain as original. Remain same with the original. The original question was 10. Here the original was 24. I'm not writing 24. I'm increasing by 1 unit, 25. Now if I increase this, what would be my optimal solution? B is 2.5 from 1. I will get 7.5. My optimal solution is 7.5, 2.5. Okay, this is my optimal solution. What would be my optimal value? (3A plus 2B is equal to 27.5. Does it increase your profit? When you increase 1 unit in your binding constant here from 24 to 25, does it increase your profit? Yes. From 27, it becomes 27.5. It's an improvement. In profit, it must increase. Your profit must increase. Okay, you are happy now because it increased. Therefore, yes, this is an improvement. This is an improvement. How much it has improved? New number minus the original number 0.5. What is your shadow price? The shadow price for C2 is 0.5. Okay, so that's how you find your shadow price. Your shadow price, the shadow price goes by binding constraint only. 2 binding constraint, 2 shadow price. Non-binding constraint, 0 shadow price. Okay, this is a shadow price. This one you can call dual value. Okay, now before I go on with further discussion, let us try to do this by the QM software. I'm going to show you how to find the shadow price or dual value in QM software. QM software. A, B, 3, 2, constant 1 is 1, here 3. I suppose now you are expert in using this QM software. Press solve here. Of course, your graph will be this. Okay, we have done this. You can double check. This is our graph. 7 3 7 3 7 3 here. Okay. This is our graph. 7 3. Now, how to find the binding shadow price? We have done shadow price for C1. Okay, remember our binding constant is first inequality and second inequality. Go here, press ranging. Okay, if you try to solve here, it will come 6 solution. Okay, 6 kind of solution. You go for ranging. In the ranging, you can see constant 1 is our binding constant. Constant 2 is our binding constant. For constant 1, look at the full value. How much is this value? 1.5. This is our value here, 1.5. Okay. Now, constant 2. How much is the value? 0.5, 0.5. There's our 0.5. That's how you compute and that's how you check. Okay. So you can check your shadow price in the QM software once you have done the computation also. Okay, double check. Just in case if you did any mistake, you can rectify that. Now, let's say your new value is 26 and your original value is 27. Okay, for the previous example, let's say you have 26. Now 26, is this an improvement? This is not an improvement. Okay, the original is 27. When you, let's say when you compute, you get 26. Is this an improvement? It decreases your profit. It's not an improvement. It's decreasing. You're not happy with that. Therefore, the difference is -1. So your shadow price, in this case, your shadow price is -1. Okay, remember that. Not improvement, negative. Improvement, positive. Okay, not improvement, negative. Improvement, positive. Okay, positive 1. I just write here 1. Okay, this is the idea of doing shadow price. Remember this. Now, for maximum, you can just follow the difference. If you're -1, shadow price is -1. If you're positive 0.5, shadow price also positive 0.5. But this doesn't happen in minimum problem. Okay, so let us do one minimum problem now. For maximum problem, which is a profit, you just follow the difference. No problem. Just follow the difference. But for minimum, it's the other way around. Let us do one. Minimum. Minimum means you must remember it is a cost. Okay, cost. For minimum, I would like to take this example. Minimum, let us take this example. Okay. In this example, our binding constraint, if we draw this, we have drawn this. Okay. In the class, we have done this exercise. If we take, if we draw this, you see the optimal solution. This optimal solution happen in between C1 and C2. So C1, C2 would be our binding constraint. Okay, C1, C2 is our binding constraint. So let me write the C1, C2. This is the binding constant C1, C2. In original question, when you solve this, the optimal solution is 3, 2, 3, 2. You can see here. Okay, optimal solution is 3, 2. And if you replace this optimal solution in objective function, you will get 48. Okay, let me write the objective function here. Objective function is 8x plus 12y. This is objective function. All right. Now let us do the analysis. This is C1, C2, which is binding constant. Right. Now let us do the analysis. I'm going to increase 1 unit in C1. Increase 1 unit in C1, that is 10, and the original for C2 is 10. So this how we do. Let me denote this as 1, 2. I'm going to solve this to get the new optimal solution by using by simultaneous equation. Minus this, you will get 4y 10, y is 2.5. From 1, my x is 2.5, 10, my x is 2.5. My optimal solution is now 2.5, 2.5. Okay, my new optimal solution is 2.5 and 2.5. What is my optimal value? My optimal value is 8x 12y is the objective function. Replace inside here. What do you get? You will get 50. When you replace the optimal solution inside the objective function, your optimal value is now 50. Now you tell me, original was 48. Remember, this is cost. This is cost. So as a businessman, you would be happy if the cost, would you be happy if the costs go higher? No, isn't it? Cost means it must reduced. Cost means it must reduce. It shouldn't go higher. Okay? In that case, if you increase 1 unit here in this resource, 1 unit, increment of 1 unit will increase your cost. Okay? Which means this is not an improvement. Okay, so if you increase 1 unit in the resource, your costs go higher. Okay, in the binding constraint. So this is not an improvement. How much it increase your cost? By 2 ringgit. Remember, original. Now your shadow price for C1 is not 2, negative 2. Okay, why negative? Because why negative? Remember, because it is not an improvement. Not improvement means negative. Okay, remember here, the one I told you here. In general, I can write it like this. Not improvement means negative, improvement means positive. Just remember like that. So in general, if this is not improvement, take the what do you call take the difference, put it here. If it is not an improvement, put here is a negative. Write it here as a negative. Let us compute for the second one, second binding constraint. This is the original. Okay, first equation I don't change. Second equation I increase by 1, 11, 1 and 2. Okay. So the original was here just now 10. I increased by 1 here. I'm going to do a simultaneous equation. Y equal to 1.75. X equal to 3.75. So the optimal solution is equal to 3.75, 1.75. What would be the optimal value? Optimal value here is 8x plus 12y you will get 51. Is this an improvement? This is a cost. The cost had increased by 51. Sorry, the cost has increased to 51. From 48, it goes to 51. So how much is increased? First, right here, this is not and not an improvement. Take 51. How much it increased? By what number it increased? 51 divided by minus y 48 3. The shadow price for C2 is 3. Is this 3? No, it's a negative 3. Why? Again, because it is not an improvement. If it is improvement, then leave it 3. Okay. In this case, cost, it is not improvement. We want cost to be reduced, not increased. Okay. That's why I say just now, for minimum is the other way around. Okay. For minimum, if you have positive here, you write here negative. If you have negative here, you write positive. For maximum, you just follow. For maximum, you just follow. Negative means negative. Positive means positive. Okay. That's how we write shadow price for the linear programming model for maximum minimum thing. Now let us check whether whatever we have done here right or wrong. Go back to the thing for QM software. I'm going to write the minimum problem here. going to write minimum problem. All greater or equal 18. Now solve, go for, sorry, this is the, because I didn't change a minimum, change minimum, ranging. You can see here first constraint, our first binding constraint -2. Just now what is our calculation? First binding constraint, you see -2. Shadow price for C1 -2, double check. Now second binding constraint, you should have -3. Go here. Shadow price for C2 is -3. So our answer is right. That's how you double check. Hope you understand this shadow price, all these things. Okay. And until here, shadow price, I told you just now, until here is chapter 2. The moment you enter range of optimality is chapter 3. Range of feasibility also chapter 3, yet to teach you, hold on for a while. Standard form, just now I teach you, very easy, change it to equation, still chapter 3. Shadow price, we just went through all these things. I will share with you the slide, you can double check. Shadow price we have done just now, also chapter 3. So all these are chapter 3. Okay, finish. Okay, this slide is chapter 2 and chapter 3. Now go back here. We have done chapter 2 and chapter 3. Chapter 4 is actually, you guys still remember this one, this slide? I sent you earlier, exercise. Okay, so chapter 4 is actually application in marketing, finance and operation management. Is actually, I'm asking you to do linear programming model in real life situation, something like this. Okay, this is your chapter 4. This exercise here, when you do, you are doing chapter 4 actually. Okay, you're practicing in a real life situation. So what to find here? Linear programming model, optimal solution, optimal value, range of optimality and shadow price. All these 1, 2, 3, 4, 5 I have teach you. Range of feasibility, hold on for a while. Okay, so you can start do all these question. Okay, I suppose you already started do all this question. There are 6 maximum problem and 5 minimum problem. The answers are given here, and you can always double check with the QM software. If you have any doubt, you always can come and ask me. This is regarding chapter 2, 3, 4. Okay, hope you guys are clear with all these chapters. Now let us move on to chapter 5. Chapter 5, distribution and network models. In chapter 5, I have went through this with you. Transportation problem, of course, for transportation problem, example 1 and 2, and transshipment problem, example 1 and 2, I went through with you representation, network representation, and how to develop linear programming model. We have done this. Okay, we have done this. After this, I also went through with you northwest corner rule and stepping stone. Modi method we never covered this time. Okay, northwest corner rule, stepping stone method I have been through with you. Okay, so let me show you how to do this in QM software. Okay, I have went through with you by manually 1, 2, 3, 4, 5 I ask you to do, and you can check the answer in the QM software. Okay, how to check the answer in QM software we will do now. Give me some time. Okay, how are we going to do this? In the northwest corner rule stepping stone in the QM software, go to module, go to transportation, go to module, transportation, new. You have 3 plants here, which means 3 origin, okay, 3 supplier, 3 source and 3 supply is the same, and 3 customer here, and 3 customer, 3 destination are same. You want to minimize the cost, click OK. So first is A, B, C, W, X, transportation cost 6, 5, 7, 3, 5, 4, 6, 7, 1, 3, 5, 1, 7, 5, 1, 7, 0, 1, 8, 0, 2, 0, 0. Okay. Once you key in all the data here, starting method would be northwest corner rule method. Okay, the one we start first, our first solution, remember, northwest corner rule method, right? Click here, northwest corner method, and solve. Go to iteration. You can play around with any solve solution you want, but I prefer iteration. It gives clear picture. If you notice here, when we do the first solution for first example, this is our solution here. You see 100 is here, 35 is here, 145 30 170 and 170. Okay, this is the first solution. If you remember our first example, there is only 2 iteration. Okay, after this there's another one. After that, that is a solution. We didn't go more than 2 solutions. Just recall back what we have done just now, the day. And then the number in the red color is your improvement index. Okay, 3, -2, 1, 1, 3, -2, 1, 1. That's how you check your answers. Okay, first. The second, let's see, I have the second or not. This is the second. You see 1, 2, 5, 1, 3, 5, 45, 1, 3, 0, 100 and 70. Okay, all numbers are here. It's just here here when I do the improvement index, I didn't take the snapshot. If you do the improvement, this improvement index for the previous one, okay, this one I forgot to erase. Okay, I forgot to erase. This is not the improvement index. But once you get the second solution, if you compute the improvement index, you should get 2, 5, 1, 1. Okay, so that's how you check your answer in the QM software. So I hope you can check all the answers in example 1, 2, 3, 4, 5. Of course, there is some typo I already upload in the group. This one 10, this one 4, and you can start do. This is until northwest corner rule method and stepping stone method. Chapter 5. If you see chapter 5 here, transportation problem, I went through with you. Assignment problem, this time I never cover. Transition problem, covered. Okay, whichever I covered means I have covered your assessment and final. The one I never covered is not coming out, don't worry. So transportation and transshipment already covered. Today, now I'm going to continue with shortest route problem. Okay, we're going to end up our class today by shortest route problem. Let us do the shortest route problem. It's quite easy. Let me close this. Shortest route problem. The shortest route problem is to find the shortest distance between an origin and various or single destination points. Okay. Now, shortest route problem. The shortest route problem is to find the shortest distance between an origin and various or single destination points. So let us say we go through this by one example. Let me give one example. Just imagine all these are some cities, okay, some town or some district, whereby we call this as node, or the circle we call this as node. All these nodes, imagine it's a city or some state. These cities are connected by roads. We call that as network. This straight line is called as network. Let's say this road, the route from city 1 and city 2, let's say it is 16 km. This is 35 km, 25 km, 12, 14, 19. This is a distance from the each town. Okay. My aim is, or our aim is, we are going to find the shortest route. If you are in town 1, what is the shortest route for you to go from town 1 to town 2? or city 2. If you are in 1, what is the shortest route for you to go to 5? You can go like this. You can go like this. You can go like this. So if you want to go to 7 from 1, what would be the shortest route? Is this, or this, or this? So we're going to find that. We're going to find the shortest route from one point to another point. Let us find that. Let us start the process. We always begin with not 1. Okay. What is the town or the knots which are nearer to 1? That would be 2 and 3. Okay, these are the nearest knot to 1. So how this 2 and 3 is connected to 1? I think there's only one way, through like this, 16 and 1. There's only one option. Since these are the only one option, and this would be the shortest route from 1 to 2 and from 1 to 3. Okay. All right. Once you identify this is the shortest route, you join with 1. And then write the shortest route here. This shortest route. So we have connected 1, 2, 3, and this thing, just imagine, is one gang now, known as connected knot. The others are unconnected knot. Okay. So the next one would be the next nearest knot, which is the nearest knot to the connected knot, is 4. How it is connected with the black color line? This is the connection. These are the route whereby the 4 is connected with 2, 1, and 3. Of course, here 12, here 35, here 15. If I want to go to 4 from 1, I go through like this, which is 16 plus 12, I get 28 here. The route, kilometer, this is distance. From 1 to 4, I have 35. From 1 to 3, I have 9 plus 15. I have 24. 28, 35, 24. Which is the shortest? 24, isn't it? Therefore, erase this one. Join the 4th node with all the others. Now next is 5, 6. How it is connected to the connected knot? How we can reach 5 from this 1, 2, 3, 4? This one. And how we going to reach 6? These are the route. Now let us solve 5 first. 5 has 25 here, 14 here. 16 plus 25. When I say 16 plus 25, I'm going through like this. 1, 2, 5. Okay. 16 plus 25, I'm getting 31. Am I right? Please correct me if I'm wrong. Not 31, sorry, 41. Now, if I use this route, I'm using 1, 3, 4, 5. So 24 times 14, I'm getting here 38. 41, 38, which one is shortest? 38, isn't it? So I'm erasing this one. Right here 38. Okay. Now let us solve 6. 17, 22. If I reach 6 from 4, I need to plus 24 plus 17. 24 plus 17, what I'm getting? 41. If I go through 3 to 6, 9 plus 22, 31. 31, 41, which one is shortest? 31. We erase this one. Okay, this is 22. Right here, 31. One gone, this one gone. The last one would be 7. This 7 is connected to the connected node. Okay, this 7 we can connect like this. 8, 19, 17, sorry, 14. If I want to go through by 5, I need to plus this. I'm getting 46. Go through by 4, if I plus this, I'm getting 43. Go through this, I'm getting 44. 46, 43, 45. Sorry, not 44, 45. 43 is the shortest. So we will choose 43. Erase this one, erase this one. This is 43. And this would be the answer for question 1. Okay, there's later I will double check, but this is the answer. If you give me this answer in the exam, you will get a full mark. Okay, don't worry. So this would be the shortest route for the network given here. Okay, let us move on to our next question. Six, 3, 4, 2. Okay, answer. As usual, we will start from node 1. The nearest node would be 2 and 3. Okay. As you can see here, the only option for 2 and 3 to connect to node 1 is, these are the only route. Therefore, this would be the shortest route. Okay, we have done the connection. Now 1, 2, 3 is one gang now, one group, connected group. The next node would be 4. 4 is connected to this group by here and here. Okay. This is 7, this is 2. If you go through 1 to 4, 7. Sorry, I forgot to do one thing. You have to write here 5. 5. Okay. If you go through 3 to 4, also 7. Okay. 5 plus 2, I get 7. 1 to 4, I get 7. So either way, you are getting a 7. So you can choose either you want to go like this or like this. The answer is correct. Either one, choose either one. So I prefer to choose this one. You can also choose this one, no problem, because it gives the same distance. Okay. Now next one would be 5. How the 5 is connected? It connected through 2 and 4. 6, 3. What is the distance? 5 plus 6, 11. 7 plus 3, 10. Which one is smallest? 10. Therefore, we erase this one. We write here 10 and join 5 to the connected group. And the last one would be 6. 6 is connected to 5 and 4. 4 here, 2 here. If I go through by 5, 10 plus 4, I get 14. If I go through to by 4, 7 plus 2, I get 9. Which one you will choose? Shortest, 9. Therefore, erase this one. Join 6 with this, and this would be 9, and this is your answer. This is your answer for question 2. We will go to question 3. Seven. Okay, let us answer this. What we have to do first, put the first node and then choose the nearest node to the first node. That would be 2 and 3. Find the root which is connecting to first node. In this case, the only root is this. Therefore, this is the shortest route. Three and 6. Next, the nearest root is the nearest node is 4. What would be the root connecting to this group? Here 2, here 4. 3 plus 2, 5. 3 plus 4, 7. I choose 5. Quite easy to see. So I didn't write in red pen. Right here, 5. Then next node would be node 5. How it is connected to the group? How it is connected to the connected group? Only one root, which is through 2. This is 2. Okay. Since this is the only root, this will be the shortest route. Again 5. Next is 6. How 6 is connected to the group? Through 5, through 2, and through 4. Okay. Here 1, here 5, here 6. 5 plus 1, 6. 3 plus 5, 8. 5 plus 6, 11. So 6, 8, 11. Which one is shortest? 6. I erase this one. Next is number 7. Node 7. How it is connected? Through 6, through 4, through 3. Okay. Here would be 4, here would be 3, here would be 9. Six plus 4, 10. 5 plus 3, 8. 6 plus 9, 15. Which is the shortest? 8. This is 8. Next would be 8. 7, 5, 5 plus 7, you get 12. 6 plus 5, you get 11. 11 is the shortest. Erase this one. Connect with this, and your total distance from 1 is 11, and the final one would be 9. How 9 is connected? Through 8, through 6, through 7. This is 2, 8, 7. 11 plus 2 is 13. 6 plus 4 is 8. 6 plus 8 is 14. 8 plus 7 is 15. So 13 is the shortest. I will erase this one. So this would be the shortest route answer for the third question. Okay. So I will, that's all for today. I will send the video and slides and some exercise for you to do practice with yourself. And next class, maybe I will let you know. Maybe next class I will explain to you the assignment and also the test, how when we're going to do the test, and maybe continue with next chapter. Okay. With that, we'll end up the class today. Thank you very much, and take care. Bye bye.